All right, you guys. I'm just gonna put my boards down real quick. Okay, so what we're doing today is this morning we're gonna go over basically the things that we think are gonna be tested in this free response, and just the things that we think are most important. Some of it from like our personal experience, maybe some of the things we like. I remember being asked of me. Whether or not that'll be asked of you, I know that it's important. So we're not going to be able to cover everything in an hour, but we are going to cover the things that we believe that are be most important. Okay. Number one, let's start with coordination complexes. That's pretty recent stuff. I know that a lot of people did pretty well on that exam, the coordination complex exam, which is great to hear. So on the board, I have 2 questions, and I want you guys, everyone that's here, to answer those. Briefly, okay? The first one is write out the name of that complex there. And then the next one is what is the chemical formula for this? Okay? So write out the name and what is the chemical formula? Okay. Give you just a few more minutes to do it. Is anybody done with number 1 already? Okay. Okay, guys. When writing out the name of a complex, what is the first step that I should probably do? What do you guys think? There are several. I'm not saying this is the way you have to be done, but what do you guys generally do? Anyone want to say, like, what is it that they do when they write out a name? They kind of go through the process.
I look at the ligands first.
You look at the ligands first, Connor. What do you do?
Yeah, I was going to say look at the ligands and determine what order alphabetically they'll go in.
Okay, so Connor looks at the ligands and then he determines which order alphabetically that they should go. That's a really good tactic as well for the first thing you should do, because I think something in naming that he brings up that's very important is that when you're naming these complexes, you put them in alphabetical order. So we've all heard this before. You've done quite a few problems on that. The second thing is figuring out, okay, what's the charge of my center atom? So not only looking at the ligands, but what are the charges on the ligands? And what is inside the coordination sphere? Is my center atom a cation, or is the complex a cation, or is it an anion? So that'll determine what type of ionic bond I'll be showing, right? Whether or not I'm showing my coordination sphere acting as an anion and coordinating with something like potassium, or acting as a cation and coordinating with something like a chloride ion. Okay. So in naming this, let's see if I can just do it really quickly with you guys. We have a couple ligands. We have ethylene diamine, which we immediately register as one of those weird ones where I can't use what? What can I use when I name ethylene diamine? I can't use my regular prefixes, and that's because in the name ethylene diamine, I have ethylene diamine, 2 nitrogens or 2 amine groups in that little molecule itself. So I can't use the regular prefixes to name that one. But I have 2 of them, so I'm going to have a bis ethylene diamine, right? I've got 2 waters, so aqua, and I have 2 bromide ions, right? So bromide, or bromo, I mean. So when we name this, we want to start off with the first one in alphabetical order, which I would say is aqua, right? So let's start with that. So we have diaqua. Diaqua, what would go next? Dibromo. Okay, and then bis, right? Bis. If I spelled this wrong, don't worry about it. I don't know if you do marker spelling, but bis ethylene diamine. And then what's my center atom? Say that again. Chromium. Okay, I just want to make sure there was some confidence there. Chromium what? Chromium 3 plus. Chromium 3, and then what's the anion here? Chloride. Okay, perfect. Okay, so there's the name. Alright, so let's move on to this next one. What is the chemical formula of potassium dialpha-dichlorobenzethyl diamine ferrate 1? Immediately, what do you notice about this name?
That's a cation first.
Yep, there's a cation shown first, right? It's potassium, and my coordination complex is an anion. So that changes things, right? It is totally possible, remember, for my coordination complex to have a net negative charge. Therefore, it'll have this ionic attraction or bond or association with another cation in solution. But when I name, I always place my cation first, regardless if that is my coordination sphere or not, right? I'm not really always placing my coordination sphere first, but rather what is the cation space anion, right? So my cation first is potassium, so I can just write that, potassium. Okay, so I have potassium and then my coordination sphere. What's my center atom in my coordination sphere? Ferrate, right? So it should be iron, and you need to be familiar with those. So hopefully this just sparks that desire to chase these down and study those names that are on his slides, like platinate, ferrate, nickelate, and those different names when your coordination sphere is an anion, right? So we have iron. Perfect. Then over here, does it necessarily matter what order I put them in my coordination sphere? No, it doesn't. So what do we have? We have two waters. So we have H2O like that. We have two chlorines, so we'll do like that. And then we have two EN. And that's everything. So there we go. That's how we do that. So you guys should very much expect to have to do a problem just like these two. One of them will be a name, and one of them will be write the formula out. So be very familiar with doing that. And so practice several problems, knowing that it's always cation, then my anion, right? Doing them in alphabetical order when you're writing out the worded name, okay? Understanding how to place the coordination sphere with something. It would have technically been wrong if I would have wrote potassium on the end here, right? Because I would have been showing that potassium was acting as an anion, and we know that it doesn't do that, right? So I did have to write it cation, anion, right? Just like this was shown, cation, anion, right? So make sure that you do that to not miss some cheap little points that you knew how to do, okay? Would you push that for me? Okay, so we'll move on. Naming is pretty straightforward. You guys, there's plenty of practice problems, and I feel like everybody feels pretty comfortable with that. Just wanted to breeze through that really quickly. Let's go over magnetism again, because magnetism is something that I think a lot of people kind of crammed for to take their exam. Maybe you forgot a couple things. Let's go over the basics of magnetism and the type of questions that could be asked. We haven't taught magnetism in a lot of depth, like you might in like a physics class, but we've taught it in enough where there will probably be a question on it that'll incorporate whether or not you understand the different types of magnetism, how they influence their neighbors, and whether or not they would repel or attract some type of magnet, okay, that gets close to it. So over here, I've drawn three types of magnets. Now the circles represent different atoms inside of that solid. So right here, we'll notice we have no arrows, right? No arrows, so we have no magnetic moments. None of my atoms are showing a magnetic moment. Over here, all of my atoms are showing one, and they're all facing the same direction. Over here, some are showing, some are not, and they're all in different directions. Over here, every one of them is anti to one another. So I have one up, and then one down, one up, and then one down, and every atom shows a magnetic moment, okay? So which type of magnetism is this? Diamagnetic. And some of this is things that you should probably just memorize, right? This is diamagnetic. I have no magnetic moments. Why is it diamagnetic? What's going on with my electrons here?
They're all paired.
They're all paired. So I would definitely know that. Diamagnetic, they are all paired. Okay? What about this one right here? This is ferromagnetic, right? Ferromagnetic meaning all of these magnetic moments align in the same direction. This is what we would call like our natural magnets, the magnets that just exist on Earth, right? They always are showing a big magnetic field. They all are facing the same direction. And then, if I bring a magnet close to this, will this change? It will, right? It'll align itself towards the magnet. So this is ferromagnetism. Does each atom affect its neighbor? Yes, that's why they're all aligned in the same direction. What type of magnetism is this? Paramagnetic. Some of them are field and some of them are not, right? But do I influence the neighbor that I'm by? I do not. So that's important to know that these magnetic moments of each atom does not influence the atom that it is next to. Will this align when I bring it to a magnet, or will it repel? It'll align. What about this one? Oh, will it repel or attract? It will repel. What type of magnetism is this? Ferry magnet. Right, this is ferry magnetism, where I have this anti to one another, this magnetic moment, okay? So do these influence their neighbors? Yes, they do actually. They do influence them to do this structure, okay? So you need to know that. And will this attract or repel a magnet? It will attract. Okay, so over here, let's do this chart really quick. Influence the neighbor, diamagnetic. No. Okay, what about paramagnetic? Influence its neighbor. No. Ferromagnet will influence its neighbor. Yes. What about ferry? Yes as well. Okay, repel and attract, diamagnetic. Repel. Okay. Paramagnetic. Repel or attract? Attract. Ferromagnetic, that one's easy. Attract. Ferry, also attract. So the only one that's repelling here is the diamagnetic, okay? So be able to stand on your own with a question like this and lay it all out there. Be able to say, what's the deal with every one of these, and whether they would, how they would act, if they influence their neighbor, how to recognize a graph.
So, with although they all, like paramagnetic, ferromagnetic, and ferrimagnetic all attract, they're all different strengths, correct?
Yeah, they're all different strengths. So you would say your ferro is your greatest. Yeah, ferro would be your greatest, then ferry, and then para, and then just repelling. So ferro, they're all aligning. So as many arrows as you can get to a line, that attraction gets greater. Remember that where these are all anti, it's harder for, like they're not aligning as strong as you would with ferro. So ferro would be your strongest. Okay. He didn't talk a lot about strength, but that's kind of the case for that. Okay, so be able to do this, jot this down in your notes, and be confident about that. Okay, this next little bit is kind of that tough stuff that we talked about, just a little bit more, that we talked about with the coordination complex stuff. We talk about isomers. It's like, oh, I hated those, right? Isomers. Isomers can be a confusing topic. We're going to go over it real quick, and the type of problem that I believe you would be asked to do. Okay, so over here, I've got a question that says draw 3 stereoisomers for the complex that I have written right here. Before we do that, why did I underline stereoisomers? Why is that important? Who can tell me why? These are simple answers. Just why is that important that I underline that for you guys to see? Connor.
It's a subcategory of isomers.
Right, it's a subcategory. It is not like, oh, isomer, okay, so I can draw a linkage, I could draw a coordination sphere. No, you can't draw either of those. This is a stereoisomer. A stereoisomer, right, is an isomer with obviously the same chemical formula, because that's what an isomer is, but it does make the same types of bonds. It makes the same bonds, right? Everything is bonded to the same thing, but they have a different spatial arrangement. So that is the definition of a stereoisomer. Same chemical formula, same bonds, but a different spatial arrangement, okay? So if I want you to draw 3 of those, then I need you to draw 3 unique ones, right? Make them different from one another of this complex right here. But I can't do linkage, right? I'm not doing linkage, and I can't do coordination sphere. That means I can't really be switching the outside one with stuff on the inside. Like I can't keep this bromide out, right? And then just do 2 chlorines on the inside. Because that would be what type of isomerism? Coordination sphere, it falls under what subcategory? Called structural, right? That's structural. So a structural isomer is something with the same chemical formula, but different bonds, right? Things are bonded to different things, okay? So atoms are not bonded to the same atoms as something as its neighbor. That's the isomer of one another, okay? So that's structural. So right now, draw 3 stereoisomers for this complex. And I'm not going to make you guys pain through it for just a few minutes. Let's just do it together. Okay, so there are several, so that's why I'd rather just have us do it together, and we can kind of look at this as a group. So the first one, I just want to throw down my center atom right here, my chromium, and then I know that it's going to be drawn like this. What are I like to do dashes and wedges because it helps me visualize like really where it is spatially. I know in our review, or not our review, but the review Dr. Macedonia did, he took a piece of paper and like drew that and like punctured a hole down the middle, and it would kind of look like a sheet of paper with that. If that's how you want to draw it, that's totally correct. I just do it like this, so if this isn't your style, just try to stay with us for just a few minutes. So we have these two ethylene diamines, and those are those bidentate ligands, so they bind in two places. Now, I've heard before, someone was saying you could bind it, well, you could do an ethylene diamine like from here to here and do a big ribbon across. Can you do that? No, do not do that. That's a point misser. You can only do an adjacent bond angle, right, with the ethylene diamine. So you would have this, and then I would do one here and make it. And then let's see what other one did I draw. And then I drew my other one here and there, just like that. Okay? And then, so I can put my bromine here, my bromide here, my chloride here. But it doesn't really matter. Right? I could have switched those two. So, and you could have switched all of them. So if I want to draw another unique one, the first one I want to do is just draw its mirror image. Right? Because I know is this chiral or achiral? This is chiral. There is no plane of symmetry in this molecule. So I just draw the mirror image real quick, because that will also count as one. And you guys should be really familiar with doing this. I don't mean like you should already be familiar with it, but get prepared to do this, is what I'm saying. Get prepared to take a complex and draw at least 3 or 4. All right? He's pretty nice in the past and not said something like draw all of them, because that's overwhelming. You're like, oh crap, how many are there? But at least 3 or at least 4, right? So that's pretty nice. So it's mirror image here. You have this. Oh wait, no, I didn't draw it here. Sorry. I was just drawing a copy of it. So its mirror image would look like this, right? See where I made that mistake? Talking to you guys. Okay, there. We're in here. We're in here. So there's another one. And then I could just do bromine on top and this on the bottom. And. Okay, so are these two chiral? Yes. What's their relationship to one another? They are enantiomers, right? That's what was being said. They're mirror images of one another, not superimposable. What about this one right here? Is this chiral? No, this is not, right? So this has a plane of symmetry right down the middle. So that just shows you that stereoisomers don't have to be chiral, right? They don't have to be. Enantiomers are always chiral, right? An enantiomer, right, that has a mirror image, both of those will always be chiral, okay? So, be familiar with doing that with any coordination complex. I recommend get with some friends, write your own coordination complex, and then say, draw me 3 stereoisomers of that, and then check them together. Have him do the same for you, or whatever you guys want to do, okay? So, this next problem, draw a compound that is optically active, then draw its mirror image. What does optically active mean? That just means it's chiral. It's another way to say this is chiral. So be ready to, if you hear that wordage, like don't get freaked out. It just means like draw something that is chiral. So in this case, if I give you the freedom to draw anything that is chiral, that's a problem you should not miss, because you can come up with it. You could draw the same one you drew for up here. Just redraw it and its mirror image, right? Because we want it's a mirror image and one of them, which we already did up here. So you could redo that if you wanted. But this is a lot of freedom, so you shouldn't go into a problem like this unprepared. Okay? So I'll just throw one up there. Just know that you guys should practice this. Okay? This is something I would definitely practice. And like this. ER. And then H2O. Okay? So if that's my guy there, is that chiral? Yes, it is chiral. So is it optically active? Yes. What does that mean that it does to plane polarized light? It bends it. Okay. Does it have a plane of symmetry? No. So it is chiral? Yes. So I'm just hammering that home so you guys can do well after your exam. So let's just draw its mirror image real quick. Drawing the mirror image should be pretty easy for you guys. So what I like to do is just draw exactly what I see on this side, just draw as the closest side here. Okay, so there we go. Bromine's in the back. This comes up to be Okay. Is this one Cairo?
Yes.
Yes.
OH2, where are you getting OH2? Oh, sorry, it's
H2O.
backwards there.
Yeah, because the bond is actually not ever made with the hydrogen to the middle, right? It's always the oxygen. So if you drew it hydrogen to the center, that's technically wrong. So you have to draw oxygen to your center, guy, because that's what's actually binding. So it looks weird. You'll get used to that. But, okay, so you guys feel comfortable with this? An enantiomer, right, is the mirror image of some sort of stereoisomer. They are not superimposable, and both of them will bend light, so both are optically active. Okay, so being able to maybe conceptually describe what optically active means, what is an enantiomer, is this an enantiomer, draw an enantiomer, those are the types of problems you're going to be asked to do. And then the last thing, before I pass it over to Corbin for the remainder of the time, is going over with coordination stuff, just the definition between high and low spin, and counting d electrons when you're asked to, like, say how many electrons are in this diagram, right? So you're given some sort of complex, you look at the ligands, and you figure out with the ligands and everything that you have a certain positive charge for the cation inside that coordination sphere, and the question would be how many d electrons are there? We kind of did that on the review sheet we did in class. So I have a couple written down on the sheet. I want you guys to look at it right now. What about cobalt 3+? How many d electrons?
6.
6. I got 6 as well. So what I want to do is hope, I don't know if the video can get that. So, okay. Follow. Yes. Okay. Hopefully it can stick. Okay, I'm just going to stand over here. It's not going to be able to get this, but what we're doing here when we're getting the d electrons, right, we have cobalt 3+. It lost 3 electrons. Anytime anything loses electrons, right, it'll lose it from its valence shell, which is that outer layer, that complete outer layer, right? So what happens here is I've got these end shells, right? 1, 2, 3, 4 on the left here, right? And that's telling me like how far away from the nucleus I am, right? So when I go to my 4th level where I notice that cobalt is, what do I call those first 2 columns? That have a specific name. Those are my s orbitals, and specifically my 4s. But then as I come to element 21 there, am I 4 what there? I'm 4 nothing. I'm 3D, right? Exactly. I'm actually not 4 anymore. I'm 3. So you guys have done this a lot in Chem 105. Just make sure that you don't forget that when you're on your exam. So the ones that I pull off first are not these far to the right. I don't start at element 27 or cobalt and take away 3 and then count the rest of the way. I always start to the left and pull left, and then count the rest of the way to the right. So if you're confused on which orbitals to pull from and everything, you can always just pull left to right, right? You can always do that. You can just read the periodic table like a book and get those right. So what about iron 3+? What is it? How many would I have, you guys? Iron 3+. 1, 2, 3, 4, 5. Yep, so we took away 19, 20, 21 electron. Boom. Counted all the way there. What about zinc 1+? How many d electrons are in zinc 1+? 10. There are 10 electrons in zinc 1+. How many electrons are in silver 1+? How many d electrons are in silver 1+? 10 as well. Okay, good. 10 electrons as well. So I just wanted you guys to see that. We have 10 electrons in the silver D1+, and we have 10 electrons in the zinc 1+. Okay? So that, and then high and low spin, as I walk back to the board, real quick. High and low spin, you guys, Corbin's going to go over in detail like how to actually do those problems. Just understanding, when I say something is high spin, that means that the spin on the electron is high in energy. So it'll always want to go to a separate level, right? They do not pair. You guys have been a lot of problems with that. High spin, they do not pair. The spin is too high. It doesn't want to go together. It will jump to the next level. Low spin is when these electrons want to pair. Their spin is low. Their energy is low. They don't have enough gas to get up to another level, so they would rather pair together and group together. Okay? So just remember those 2 definitions. High, there's too much energy to pair them. Low, there's so little energy that they just pair together. Okay? So keep that in mind when you solve these problems. that Corbin's going to go over, and always be able to count the d electrons and write out a diagram. If he ever says, oh, write out a diagram for this, that's just the tetrahedral or octahedral diagram that Corbin's going to go over. So I know sometimes we've been asked that question. I've seen some students struggle to understand like what they needed to do, and it's that simple. Write the diagram is octahedral complex or tetrahedral complex, okay? Does anybody have any questions about that? No? Awesome.
Okay, so the first thing I want to go over is all the ins and outs of voltaic and electrolytic cell. I'm just doing voltaic and electrolytic. In our last review, I went over concentration cells. So if you want a refresher on concentration cells, just hop on YouTube and watch that last video. This is something that I would definitely be able to do for your exam. It even says on the necessary skills list, be able to construct your own voltaic and electrolytic or concentration cells. So I want to just go over all the ins and outs of these so you guys don't miss any points on this on your exam. So, first of all, this is the reaction that they gave you, all right? The first thing I want to mention is anytime you see a redox reaction, you guys should automatically start thinking about reduction potentials. The one that has the most positive reduction potential is going to be the one that's reduced. The one that's most negative is going to be oxidized. But the thing is you can't get in such a robot mode that you just only think about reduction potentials. You have to look at the reaction they gave you. So if they were to potentially give you a reaction where what was most likely going to be oxidized is now reduced, do it as reduced. So I'm going to do some problems later where we calculate our E naught of the cell where you do cathode minus anode. It's always cathode minus anode. Don't get glitched and start thinking that one is going to be oxidized when in the reaction it tells you it's going to be reduced. So always look at the reaction they gave you. So in my reaction here, I have copper being oxidized and silver being reduced. So let's do a voltaic cell first. I always start with voltaic cells, and then you'll see electrolytic cells that are very similar. It's just opposite in a couple areas. So the first thing, what is going to be on my anode? What is going to be the metal on my anode? Copper, right? Because copper is being oxidized. So I have copper solid here, and this is my anode, and this is my cathode. Okay, so if I have copper solid on my anode, what's going to be on my cathode? Silver. Perfect. And I already drew a couple of these up here. The charges on the anode and cathode. For a voltaic cell, we know a voltaic cell is something that happens spontaneously. Yeah.
For the silver, it shouldn't be plus, it just should.
Oh, I'm sorry. Yeah, you're right. It should just be solid on that. So, a voltaic cell is something that happens spontaneously. The reason it happens spontaneously is because electrons are negatively charged and they're naturally drawn towards the cathode, the positively charged. So just know in a voltaic cell, the cathode is what's positive, okay? So, second thing is what's happening here on the copper. It's being oxidized, right? So what's happening is when copper is being oxidized, little copper ions are being emitted or being shot off of the metal, okay? So we're getting copper 2+ ions coming off of that metal piece. Now, I just want to talk about the salt bridge here. The salt bridge has been confusing for a lot of students, knowing which one is positive, which one's negative, where each ion goes. And it can be confusing when we have different charges up here. Just think about it like this. On the anode side, if I'm building up a positive charge in my solution, then I'm going to want to neutralize that with negative. Okay? So my salt bridge, the anions are going to want to come in where I'm building up this positive charge. So the copper ions are being put into solution, so my nitrate ions are going to come down from the salt bridge. And here, it's the exact opposite. We have silver ions that are being reduced, so they're getting kind of plated onto that silver cathode. And in that case, we're losing positive charge in our solution, so my cation in the salt bridge is going to want to come down in and make up for that. Now, anytime we do cells, you have to have an anion in there as well. So the easiest way to do it is just to do sulfate. We use sulfate a lot with copper sulfate, silver sulfate. So just make sure you have an anion in your solution as well. And now the last thing is to figure out where the electrons are flowing here. So we know in a voltaic cell, it's a spontaneous reaction. So here our electrons will be driven to the right. Does anyone have any questions on this? You guys should be very familiar with this. You just took the exam yesterday. Good? Okay. So let's do electrolytic cells now. Electrolytic cells are basically the same exact thing, except our electrons are flowing in the opposite way. And this is how your cell phone and batteries work, is that when your cell phone is running during the day, that's a spontaneous reaction. We're getting energy out of the phone just because of the nature of the cell, right? Our electrons can naturally flow towards the cathode. That's spontaneous. However, when we recharge our cell phone, we need a power source. So we plug in our cell phone to get that power source. What you can actually do with a cell is reverse the flow of electrons. So we can actually build back up our charge over here. So when we unplug our cell phone, it can naturally just go again. So the first thing I do when I see an electrolytic cell is say, okay, if my electrons went that way in voltaic, I know for sure my electrons are going to go this way in my electrolytic cell. If this is the case, which one is now being oxidized and which one's being reduced? Where are my metals going to be?
The metals stay in the same place.
Yes. Yep. Metals will stay in the same place. So we have silver and copper still, right? And the only thing we're doing now is we're reversing the reaction. So we know we're going to have copper 2+ ions in our solution here. We're going to have silver ions here. So which one is now the cathode and which one is now the anode? Yes, copper is the cathode. Because what we did is we're reversing the reaction. So now these copper ions are going to be reduced while these silver ions are going to be oxidized. And one thing to be sure is don't get in the habit of always seeing the anode as a negative charge. When we construct our cell in an electrolytic cell, the charges stay the same. So you can think of the charges on our anode and cathode like a battery. They're just always in the same spot. But what we can do is just reverse the flow of electrons. So our anode and cathode change just because the definition of an anode is what's being oxidized. The definition of a cathode is what's being reduced. But our charges will stay the same between both cells. So what's happening here is I have silver being oxidized, right? So for every silver that's oxidized, I have one electron that I have excess on this metal. So now my electrons are going to be flowing through the wire, and they're going to be landing here on the copper metal. With excess electrons on the copper metal, these ions are now going to want to be reduced. They're going to want to come and stick onto the metal. So, what's going to be happening with my salt bridge here?
Reverse from voltaic.
Yeah, it's reversed from voltaic. So at the anode site, I'm building up positive here, so I'm going to want to put negative in, right? And on my cathode side, I'm reducing, so I'm losing positive, so my positive cation is going to want to come in. And that's basically all you have to know about electrolytic and voltaic cells. Know how to construct them, know the different parts, know the way the electron flows. Does anyone have any questions on this? Okay.
Corbin, what's the curveball they could throw on that?
The curveball, it's really straightforward. I think maybe the biggest thing is looking at the reaction given. Look at the reaction given and see what is oxidized and what is reduced. Don't go straight to your reduction potentials and say, okay, well copper's pretty low, it's probably going to be oxidized. Where in the reaction they could potentially give it to you as being reduced. So just always make sure you look at the reaction given, and that's what you roll with. Yeah.
So if you were to end up with like the negative value, like let's say I can switch, whatever, like does like the weird way, is that still the voltaic cell or would that now be the electrolytic cell? Because wouldn't it require energy for that flow?
Yeah. So if you got a negative value for your for your E naught of the cell, it wouldn't be a voltaic. It would not be spontaneous. So most likely it is an electrolytic cell that's going to have energy plugged into it for it to work. But it's not. Electrons won't flow from that spontaneously. Okay? Hey, we're good? So now I want to do the same exact reaction that we did up here. I want to calculate a few things you guys have been doing for that cell that we built. So we just built our own voltaic and electrolytic cells, and now I want to know what our E naught of the cell is, what the delta G of the cell is, and what the E of the cell is at 0.5 molar if we use 0.5 molar solutions for both. So let's start out with the easiest one right here. And just so you guys know, EMF, you may have seen it before, it's the same thing as just E. So this is just like our E naught. So E naught is cathode minus anode. So I gave you the reduction potentials right here. Silver is 0.7996, copper is 0.342. So that being said, we would assume that silver would be reduced because it has a higher reduction potential. But let's check in our reaction to make sure that is the case. Is silver being reduced? Yes, it is. Okay? So I know I can take 0.7996 for my cathode, and I'm going to subtract that from 0.342 at the anode. And the answer you get there is 0.4576 volts. Okay, everyone good there? That's, really basic. So let's move on and calculate the delta G. Anytime you see delta G, what equation do you think you're going to use? That should just be automatic. Yep, I always just use this one. There's a few different ones you can use. I use delta G equals negative NFE. Right? So we have all the information we need just from our reaction and calculating this to solve for the delta G of the reaction. And we assume that it would be spontaneous because we have a positive voltage for our EMF of the cell. So let's see, if we have a positive for this, then our delta G should be negative for it to be a spontaneous reaction. So we have delta G equals negative, how many electrons are being transferred here? 2. So we have negative 2 times Faraday's constant, 96485, times our E naught, which was 0.4576. And when you do that, delta G should equal negative 88.3 kilojoules per mole. So that rings true. Our delta G was negative when this was positive, so that is a spontaneous reaction that's happening. Everyone good there? Okay, let's go on and do this one. I think this is the most tricky one because we get in these modes of like, oh, I know what to do, I know what equation I'm going to do, but you'll miss little tiny steps. Okay? So what is the EMF of the cell if 0.5 molar solutions were used for both? So this automatically tells me I'm at non-standard conditions. So anytime you're at non-standard conditions, you're going to use this equation. And there's a couple different ones you can use. I'm just most comfortable using this one, so that's what I'm going to do. You have the E cell equals E naught minus 0.0592 over N, which we already knew was 2, times the log of Q. So, we know our E naught was 0.4576, so I'm just going to fill that in. And now we have everything we need because we have concentrations to solve for our E cell. So let's just go ahead and set up our log part. So we have log, so anytime, you guys should know this with equilibrium, we've done this so much. Anytime you have a Q or a K, it's products over reactants. And you don't include solids and pure liquids in those. So let's go to our reaction. What's our product?
The copper.
Copper ion, and our reactant was silver ion, okay? These are the only two that are aqueous in this solution. We don't include pure solids and pure liquids in our Q and K, calculated for Q and K. So let's just go over and fill that in. So I have the log, and they told me it was 0.5 molar solutions for both. So products over reactants. Copper is going to be first, 0.5 over 0.5. Am I done? No, because there's a coefficient right here in front of silver. So don't forget, when you have coefficients in your reaction, this needs to be squared.